Hi everyone, my name is Roy Lipman. As Itamar said, I am the lead developer behind the Redis graph project. I've been working on this graph database for about 2 years now. This talk is going to be splitted between myself and Jacob from Xblog, and I will try to explain what's going on behind Redis graph. What are the internals? What are the concepts that Redis graph is built on? And hopefully, I will be able to convince you that using math, more specifically linear algebra, has a lot of benefits to it. All right. So I've took this picture yesterday evening, just before I left the office. So this is a view to Ayalon, and it made me think about how lucky I am that I can walk from the office back home, so I don't have to deal with all of this traffic. But it also made me think about all of those people stuck in traffic using Waze. I'm not sure why they need Waze. They're going to be stuck in traffic, but I thought about, are they aware of the fact that behind the scene, they're all using graphs? So just a number of use cases where you will see graphs, specifically for the domain of transportation. So the first one is, find me the cheapest path to go from point A to point B. So Waze are doing it, Google Maps are doing it. The second example is delivery optimization. So for example, Amazon, UPS, FedEx, they all build a route which is the most optimal route for their delivery guys to drop off their packages. And the last one is social commute. So companies like Uber and Lyft, if you ever use their shared ride, then they're basically computing an on-demand route. So people might want to join an ongoing ride. So all of these, behind the scenes, are using graphs. And so really quickly, what is a graph? So a graph is basically a set of nodes. Each node can represent whatever you want, and those nodes can be connected with edges. So you can think about nodes in a social network representing people, and edges connecting two different persons in case those persons are friends. And so there are basically two ways you can represent a graph. This is the most common way. This is what everybody is doing, an adjacency list. And the idea behind an adjacency list is that every node in the graph maintains a list of its neighbors. Usually, the list itself is a linked list because the list of neighbors is dynamic. I can connect two nodes and I can disconnect two nodes, and so I want this structure to be dynamic. And this is what everybody's doing. Once you have the graph structure, one of the basic operations that you're doing with graphs is traversing. You will see traversal all over the place. And so one of the most common ways to traverse a graph is the breadth-first search traversal. Basically, I want to see which nodes can be reached after doing 1, 2, 3, or n hops away. And the idea is I take the node that I want to start my traversal from, let's call that node S, starting point, and we put it into a queue. And as long as this queue is not empty, I'm removing an element from the queue. I'm inspecting this element. This is basically a node. I'm inspecting its adjacency list. And for every node which this node is connected to, a node within its adjacency list, I just make sure that I haven't visited that node already. And if not, I'm just putting that node into the adjacency list. And so this way, I traverse the graph one level at a time. the key thing to take away from this example is that this algorithm is linear. You're always focused on a single node. An alternative. So this is what Redis graph is doing. It represents a graph using a matrix. And so this is just a simple example graph that we will be working with, just to give you the idea of how you can represent a graph using a matrix. And so both the rows and the columns of the matrix, they are mapped back into nodes. So for example, node number 1, node with ID 1, is represented by row number 1. And if node I is connected to node J, then the ij entry within that matrix will have a 1 in it. So here we see that node 1 is connected to node 2. And so we will have a 1 representing that connection in the in the first row, second column. That's the entire idea behind matrix representation of a graph. You have the entire graph structure within a single table. So once we have that representation, how do we traverse the graph? So it turns out, to traverse a graph, all you have to do is to take that matrix representing the graph and multiply it by itself. So this will do a 2-hop traversal. Who here find this oddly surprising that matrix multiplication would do graph traversal? Just a few. Okay. I find it oddly unbelievable. Anyhow, so the first time I've seen this, I was extremely surprised. I did not exactly understood why matrix multiplication does graph traversal. So here's why. Let's just focus on that first node that we've seen. Let's just focus on node 1 going to node 2, and from node 2 you can reach node 3. So 3 is a second level neighbor of node 1. So why does this work? We're taking row 1 representing the connection of node 1. We're multiplying it by the matrix. So we can do the row column multiplication for those of you who have done linear algebra, but another way to think about this multiplication is to take every entry within that vector to the right here and multiply the value at entry I with row I. And so for the first entry, we have a 0 times the first row, which is basically just a 0. And then we have a 1, which represents the connection between node 1 to node 2. So take that 1 and multiply it by the second row. And this is the key idea. 1 has access to 2. 2 is basically the second row in the matrix. So 1 has access to 2's neighbors via node number 2. So once we're multiplying that 1, representing 1 connected to 2, with 2's neighbors, you're getting all of the neighbors that are 2 hops away. And the rest of the multiplication is just zeroed out. And so we're just summing up those matrix vectors, and we're getting the result. The first row in the resulting matrix describes the 2 hops neighbors of node number 1. And so we can see that we have a 1 at the third column, which is exactly what we're expecting because you can reach node 3 from 1 after doing 2 hops. So this is nice. A couple of really nice properties that we can take advantage of. Matrix multiplication is extremely scalable. So for example, we can take this matrix multiplication and break it into 2 multiplication. We're taking the matrix and just split it in the middle, and A times B all of a sudden turns into A times B1 concatenated with A times B2. And this will basically give you the result. So you can think about using multiple threads to perform this matrix multiplication. Another thing to notice is that matrix multiplication is an associative operation. So if we want to multiply a number of matrices, you can take a bunch of multiplication and perform them on one thread, and then take another batch of multiplication and do these on the different thread, and just combine the result with another multiplication. So these all can be done on the CPU, but today we have GPUs. So we're not limited to 16 threads. We can have each individual entry of the resulting matrix to be computed on a single GPU thread, and we have hundreds of thousands of those. So each GPU thread will compute a single entry, and all of the multiplication will be done instantly. Redis graph is using Boolean matrices. So we only care, the values that you would see in those matrices are ones and zeros. And so if you recall, if you're trying to multiply two vectors, this is a dot product, the way that you would do that is you're taking entry at position I from vector A, and you multiply it by entry I at the second vector, and you're just summing up those multiplications. And if you have vectors of really long vectors with millions of entries in them, this computation can take a while. But if we're dealing with Boolean algebra, if we only care about if the bit is on or off, once we have an AND operation, so basically multiplication is done by AND and addition is done by OR, once we computed a 1 and 1 gives you a 1, we don't care about the rest of the computation because it's just ORs between them. Once we have a 1, we can stop early computation and conclude that the value of this multiplication is just 1. So this is Redis graph. It performs traversals in order to answer queries, and it does that by producing linear expressions and then just evaluates them. It is a property graph database. The idea is that you have nodes that can represent anything that you want. Nodes have attributes. So for example, you can have a node representing some person. That person can have a name. That person can have an age. And you have basically edges to connect different nodes, and those edges can also have attributes or properties attached to them. So here's an example of a query. Find me or consider every person in the graph who is over 30 and finds its friends of friends who are 2, 3, and 4 hops away from it. So this query is written in Cypher, one of the most popular graph database query languages out there. And what Redis graph does is it takes this query and it transforms it into a linear expression. And so this is the expression that Redis graph is going to evaluate. We would have a filter matrix representing everyone in the graph who is over 30, and then just multiply it by the friendship matrix raised to the power 2, 3, and 4, all added up together. So this is the computation. FOF is the end result. And so how does this method scales compared to what everybody else is doing? So we've done a benchmark. The benchmark included a graph with about 42 million nodes and roughly about 1.5 billion edges. And the query that we've run is counting how big is the neighbor of some given nodes, and we're considering neighbors who are k hops away, and we're considering 1 hop, 2 hop, 3 hops, and 6 hops away. I'm only sharing the result of Redis graph against one of the most popular graph databases out there. And so for just a single hop to compute how many nodes can be reached, we were able to do that in under a millisecond, while the competitor was able to do that within about 200 milliseconds. 2 hops, it took us half a second, while the competitor did it in 18 seconds. 3 hops, we did it in 9 seconds. Competitor, I believe it's 5 minutes, and lastly, 6 hops away, just above 1 minute, and the competitor just did not reply. That's it.